Before we square any numbers, let's make sure you're up to speed on multiplication. What's 8 times 3? Or click here to review. Right, 8 times 3 equals 24. Next, let's try multiplying a number by itself, like 7. So what's 7 times 7? Nicely done. So 7 times 7 equals 49. Multiplying numbers by themselves is pretty common in algebra and geometry, and there are a few different ways to say it. You can read this as 7 times 7 equals 49, and another way is to say that 7 squared equals 49. When you say you're squaring a number, that means you're multiplying it by itself. This term actually relates to square shapes, but we'll save that for a geometry lesson on area. If we multiply 2 by itself, we get 4. So 2 squared is 4. Now numbers like 49 and 4 that you get from squaring whole numbers are called square numbers. So take a look at these 4 numbers down here. Which of them are also square numbers? Right, 16 equals 4 squared and 25 equals 5 squared. So here's a list of the first few square numbers from 0 to 49. Let's take a closer look at 3 times 3. Now another way to write down that you're squaring a number is like this, with a 2 up and to the right of the number. So this expression is the same and also equals 9. You can read this aloud as 3 squared equals 9. And yet another way is to say that 3 to the second power equals 9. Because this number up here is 2, that means you're multiplying 3 by itself a total of 2 times. If this number were 4, for example, it would mean you're multiplying 3 by itself a total of 4 times. Let's hold on to this example up here. And next, try evaluating these 3 expressions: 8 squared, 9 squared, and 10 squared. Excellent. So here are the squares you found. And what happens when you square a negative number, like -4? In other words, what's -4 times -4? And to review multiplying negative numbers, click down here instead. Precisely. So the square of -4 is 16. In general, squaring a negative number always gives you a positive number because the 2 minus signs will cancel out. Finally, you'll often see expressions like this: 6.3 squared. It's kind of a pain to multiply 6.3 and 6.3 by hand, so you'll want to use a calculator like the one down here. If you open the calculator, you can evaluate this as 6.3 times 6.3, or you can also just type in 6.3 and then press this button down here, which lets you enter powers, and then type in a 2. So now we have 6.3 squared. Pressing the equal sign gives us 39.69, and that's our answer. 6.3 squared equals 39.69. You might also see powers written like this. Instead of up and to the right, it's directly to the right of this symbol called a caret. Powers are usually written this way when it's too difficult to format it like this. But these two expressions mean the same thing. So for your final challenge, use the calculator to evaluate this expression, 1.7 squared. Here we'll explore raising numbers to a whole bunch of different powers. But first, try evaluating this expression, 4 raised to the second power, which you can also read as 4 squared. Exactly. Because this number up here is 2, that means you're multiplying 2 4s together, and 4 times 4 equals 16. So again, this equation says that 4 to the second power equals 16, or 4 squared equals 16. Now what happens if we make this number a 3? Well, then we're multiplying 3 4s together, so 4 times 4 times 4. This product equals 64. So 4 to the third power equals 64. And just as raising to the second power is also called squaring, raising to the third power is also called cubing. So 4 cubed equals 64. Next, try evaluating this expression. What's 5 to the third power, or 5 cubed? Exactly. 5 cubed equals 5 times 5 times 5, or 125. Next, try evaluating this expression, which you can read aloud as 3 to the 4th power. Right, 3 to the 4th is 3 times 3 times 3 times 3, or 81. Now let's quickly introduce the names for the terms in this expression. This whole expression, 3 to the 4th, is known as a power. This number up here, which says how many times you're multiplying, is called an exponent. And the number down here that's being multiplied by itself is called the base. So go ahead and quickly identify the base in this power and the exponent in this power. Exactly. The base in this power is 5, and the exponent in this power is 7. Now let's look at a real-world example. Suppose you're looking at bacteria under a microscope. In a relatively short amount of time, a few bacteria can become thousands or even millions. So suppose you start with a single bacterium at noon, and it doubles or splits into 2 every hour. So at 1 p.m. you have 2 bacteria. And by 2 p.m., both of these have divided into 2 more, so we have a total of 4 bacteria. By 3 p.m., they've doubled again, so now we have 8 bacteria. And they keep doubling every hour. Here's 5 p.m., 6 p.m., and 7 p.m. So how many bacteria do you have at 7 p.m. after they've been dividing for 7 hours? Precisely, after 7 hours, there are 2 to the 7th, or 128, bacteria. That may not sound like too many, but after just 1 day, or 24 hours, there are 2 to the 24th bacteria, which is more than 16 million. So doubling every hour may not sound that fast, but before you know it, you have millions of bacteria on your hands. Next, let's look at powers of negative numbers, like -2 to the 3rd power. That means we're multiplying -2 by -2 by -2. Multiplying the first two gives us +4 times -2, which equals -8. So -2 to the 3rd power equals -8. Next, try evaluating a few more powers of negative numbers. Nicely done. So here are the answers you found. You might have noticed a pattern. Raising a negative number to even powers, like 2 and 4, gives you a positive result, while raising to odd powers, like 3 and 5, gives you a negative result. Next, see what happens when you raise 0 to different powers and when you raise 1 to different powers. Right, so 0 raised to any power will always give you 0, and 1 raised to any power will always give you 1. Next, let's look at raising decimals, like 2.7, to powers. So if you were asked to evaluate 2.7 to the 4th power, you'd probably want to save yourself some time and use a calculator, like the one down here. So first, you can type in 2.7. Then press this button over here to raise to a power, and then enter 4. Pressing the equal sign will evaluate this expression, and the answer turns out to be 53.1441. So try evaluating 1.3 to the 5th, and again, feel free to use the calculator. Great, so 1.3 to the 5th power equals 3.71293. Now all the powers we've been looking at so far have been 2 or greater, but what's 7 to the 1st power? Well, that means we're multiplying together exactly 1 7, so that's it. 7 to the 1st power equals 7. See if you can evaluate these other expressions for which the exponent is 1. Don't worry, there are no tricks to this question. That's exactly right. Raising a number to the 1st power never changes the number. Let's summarize what you've discovered here. If you raise negative numbers to different powers, you'll get positive or negative results depending on whether the power is even or odd. You found that 0 raised to any power equals 0, and 1 raised to any power equals 1. You got some practice raising decimals to different powers, and finally you found that raising any number to the first power gives you that number back. And in later lessons, you'll explore what it means to raise a number to the 0th power, a negative power, and powers that are not whole numbers. Here we'll introduce square roots, but first try evaluating this expression. What's 6 squared? Right, so 6 squared is 6 times 6, which equals 36. Square roots are like working backwards. When you see this square root symbol, it means you're looking for a number whose square equals the number inside the root. So what number, when you square it, gives you 36? Well, that's 6. And you can read this equation as the square root of 36 equals 6. Try another example. What's the square root of 81? In other words, what number, when you square it, gives you 81? Exactly. The square root of 81 is 9, because 9 squared equals 81. Next, try getting a little more practice and evaluate these 4 square roots. Excellent. Looks like you really got the hang of this. Now we said the square root of 36 is 6 because when you square 6, you get 36. But there's actually another number that you can square to get 36, and that's negative 6. When you multiply two negative numbers, the minus signs cancel out, so negative 6 squared also equals 36. If you'd like to review why that's true, click down here in a minute. So even though squaring both these numbers gives you 36, square roots are always defined as being positive. So the square root of 36 is positive 6, not negative 6. Now sometimes you'll see a minus sign in front of the square root. So this is the square root of 36, and then you're making it negative. So this equals negative 6. Next, try evaluating these expressions, some of which have minus signs in front. Excellent work. So here are the answers you found. Next, we'll combine squares and square roots. Let's start with the number 4, square it, and then take the square root. So 4 squared is 16, and the square root of 16 is 4 again. So we started with 4 and finished with 4. Try evaluating a few more expressions like this. For these two, you're squaring a number and then taking the square root. And for these two, you're taking the square root first and then squaring. Exactly. So for each of these, it looks like squaring and taking a square root seem to cancel out. Does this always work? Try evaluating one last expression. Start with negative 7, square it, and then take the square root. Right, so negative 7 squared equals 49, and then you're taking the square root. Square roots are positive, so this equals positive 7. So here, the square and the square root did not quite cancel out. We lost a minus sign in the process. Squaring and taking a square root will often cancel out, but be very careful when you're working with negative numbers like this. So the square root of 25 is 5, and the square root of 36 is 6. But what about for numbers in between? For example, what's the square root of 31? Don't worry, we'll take square roots of numbers that are not square, like 31, in a later lesson.